Hey guys, Kenna here, and so I'm just going to do a really quick hit here on air resistance. We've spent most of the unit really neglecting air resistance when we go ahead and do our projectile motion or when we start looking at any of our gravity calculations. But in real life, this is not feasible because, especially in larger objects and fast moving objects, air resistance is definitely something that needs to be included. So, today I want to go ahead and take a look at the impact of air resistance on free fall problems and talk a little bit about what features of an object air resistance depends upon. And so, as we go ahead and go through today, we'll make this really brief. I want you to be thinking about every calculation we've done that doesn't include air resistance, that neglects it, and how that would be different if we did include air resistance. Let's start out with a little quick review on free fall. So let's imagine there is no air resistance. Shouldn't be hard. That's what we've been doing. So an object moving under the influence of gravitational force only is said to be free fall. And if that is the case, it is accelerated under g, which is 9.8 meters per second squared. But again, remember that this is all only true if we are neglecting air resistance. Now, hopefully you've watched the video where we went ahead and went with Brian Cox to the vacuum chamber, and you got to see them go ahead and drop the bowling ball and feathers that were of the same mass. Now, the first drop went just as you would expect it to in the presence of air resistance. But when he did the second drop and dropped a feather and a hammer without air resistance by removing all of that air in a vacuum, they accelerate equally. Okay, and we even saw them strike the ground at the same time. The force of gravity is the only force acting on these objects. Projectile, right? No atmosphere means no air resistance and no drag force. So the surface area and weight makes no difference at all. Okay? All objects fall at the same rate if we drop them into a vacuum tube. However, as you saw with the first drop, the feathers drop a lot slower than the bowling ball because of air resistance. So, what is air resistance? It's a force caused by air molecules opposing the motion of the object as it goes through the air. In reality, this is a form of friction. Typically, we call this drag. You can experience this if you're ever driving down the road and you stick your arm out the window of the car with your palm facing down, and then you lift your palm so it faces forward part of the car. And what does that do to your arm? It pushes it back. And so you're experiencing the impact of air resistance. There's not a whole lot when your palm's down because your surface that's striking the air is pretty small. But as soon as you increase the exposed surface area, you're going to feel a lot more of that drag force or air resistance. So the amount of air resistance force on an object experiences depends on its speed and on the exposed surface area. It does not depend on the weight of the object. All right, so remember, velocity is a big deal. The faster the object's falling, the more air molecules are hitting it, therefore we're getting more air resistance. The greater the exposed surface area, okay, the more surface there is to hit, and the greater the air resistance there. Now, let's think about this in terms of skydiving. When you skydive, your body is providing the surface area. If you were to just go and have your feet going before the rest of your body, you would have a fairly small surface area. But if you were to lay out flat with your arms and legs extended fully, you are going to have the maximum amount of surface area. So this is an important thing to kind of keep in mind. Okay. Watch the jump of Felix Baumgartner that we have if you have time. It's optional. And as you go ahead and take a look at that, look at the speeds that we're talking about and think about how much air resistance exists there. Okay. Here's a body that's skydiving, and you can kind of see what we're talking about in terms of surface area. The other thing I wanted to introduce to you is this idea of air density and terminal velocity. So let's begin with air density. So air density Objects that fall through the atmosphere experience two forces. One, the weight downward, and two, air resistance or drag going upward. Because gravity is an acceleration of g 9.8 meters per second squared, as the object falls, its velocity increases. As its velocity increases, so does its air resistance. And the object's rate of acceleration decreases until it falls at a constant velocity. So if you can imagine the force of gravity pointing downward and air resistance opposing it or pointing upward, remember it's a form of friction. And so at some point, the faster and faster you go, you reach a point where the air resistance becomes so large that it balances out the gravity and you stop accelerating. At this point, this is what's known as terminal velocity. Okay, so as an object falls, its velocity increases. As velocity increases, the air resistance increases. And eventually, the air resistance will grow until it equals the force of gravity. At this point, the forces are balanced. There's no more acceleration, and we call this terminal velocity. So when we start thinking about this, we also have to think about what happened in terms of the space jump that hopefully you'll watch the video for, because we think about the speeds that he reaches. And this is only possible because there's so much less air resistance at higher altitudes because the air is thinner up there. Then you start thinking about what happens with a parachute. Parachutes increase the cross-sectional area, so more surface area, thus creating more air resistance, thus slowing your descent. So the force of the air resistance and the force of the gravity become balanced much sooner. You reach terminal velocity faster, and therefore you have a slower descent. When you first pull the chute, you may actually have a short period of time where the air resistance is greater and the acceleration stops altogether until those forces balance out. But then you descend under a much safer terminal velocity. Okay, guys, that's all I've got for you today. I hope you do well. Take care of yourselves. Stay safe, stay healthy, and I'll see you soon. Take care. Bye bye.